in 1 liter, okay? All right, so what are our normal electrolyte levels? Well, we have a table here. This is table 9.6 in your textbook, just showing you concentrations in, notice the unit, milliequivalents per liter. So it's literally just like, you know, moles per liter or some kind of concentration. It's just in milliequivalents, because we're not talking about the identity of sodium. We don't care that it's sodium. We care about the amount of charge, okay? So we're just looking at the charge here, or communicating concentration of charge. So anyways, you can see we need quite a bit of sodium, okay, in our blood, way less amounts of calcium and potassium, and not very much magnesium at all. We need quite a bit of chloride, which provides negative charge in our blood, a little bit of bicarb, and then sulfate and HPO4 with the 2- charge as well. Just a little bit of those contribute to the negative charge content of our blood. So to unpack this some more, let's work some problems. You will definitely need to be able to do problems similar to this with equivalence and understanding equivalence. So here's the question. How many moles of aluminum cations are needed to obtain 1 equivalent of aluminum plus 3? So if we look at this, remember that 1 equivalent equals 1 mole of charge. And in fact, let me go back and write of plus 1 charge. All right. So let me ask you this question. If we have 1 mole of Al plus 3 cations, how many moles of charge do we have? If we have 1 mole of aluminum plus 3 cations, we have 3 moles of plus 1 charge. Okay? Because each cation carries a plus 3. If we have 1 mole of these cations, we have 3 moles of plus 1 charge. So if we just want 1 mole of plus 1 charge, we want 1/3 of that, we just need to divide this by 3. Okay? We don't want 3 moles, we just want 1 equivalent here, and 1 equivalent is 1 mole, so we're just going to divide this by 3, which would give us 1/3 of a mole of Al plus 3 is going to be equal to 1 equivalent, okay, of plus 1 charge. All right. This might be blowing your minds for some of you, but hang with me. You've really got to just practice this stuff to get comfortable with it. We don't talk about these terms a ton. So let's look at another question. How many moles of fluorine are needed to obtain 1 equivalent of fluorine? So just like we can have a mole of positive charge, we can have a mole of negative charge. Okay, fluorine is an anion, carries a negative charge. 1 equivalent is still 1 mole of charge, and it doesn't matter. Honestly, if we scroll back up, it doesn't matter if the charge is plus or minus. Okay, it doesn't say. It just is 1 mole of charge. Charge can be plus charge or minus charge. So 1 equivalent here of fluorine, well, we know 1 equivalent period equals 1 mole of charge. It's just in this case we're talking about negative charge since we have an anion. Okay, so if we have 1 mole of F minus, and each ion carries 1 minus charge, then we have 1 mole of minus charge. Okay, so 1 mole of fluorine anions equals 1 mole of minus charge. That equals 1 equivalent. Okay, so how many moles do we need? Just 1. Just 1 mole of F minus equals 1 equivalent. All right. Let's see here. If we had, well, we'll move on for time's sake, but if you want more problems like this, definitely email me, or I can try to provide some let me look at the back of chapter 9 and see what is available for practicing calculating equivalence as well there. So that's equivalence. I'm going to briefly hit on this topic before we get to osmosis. These next 2 slides, or 3 slides rather, are not the bulk of chapter 9. They're kind of one of the smaller topics in chapter 9, but I still think it's worth mentioning. Since we're talking about solutions, one important property of solutions is that you will find they have an elevated boiling point, and if you look down at the next slide, they have a lower freezing point. Okay, we call that elevated boiling point and a freezing point depression. Why? Why do solutions have a higher boiling point than pure substances and a lower freezing point than pure substances? And in fact, that's what this graph is showing right here. If you look at it, I'm going to circle, here's the boiling point of water. If we drop down, okay, we know it's 100 degrees Celsius. And if we have a solution of NaCl, in fact, it's a 1 molar solution, and we circle its boiling point and drop down, we see that it's not a huge wow factor here, but it's higher by a degree. It's 101. It boils at 101 degrees Celsius, and pure water boils at 100 degrees Celsius. So not a huge change there, but it is a higher boiling point. Okay, so the question is, if we read down here, why does pure water have a lower boiling point? Or in other words, why does a solution of sodium chloride have a higher boiling point? And the answer is right here. Overall, it has to do with vapor pressure. We don't have to fully understand that, but solutions have a lower vapor pressure. Why? In solutions, there are more intermolecular forces, I'm going to abbreviate that, holding solute and solvent particles or molecules together. Okay, it's just like there's a little more glue holding everything together. So it takes a little more energy to bust up those intermolecular forces, or that glue, in other words, and cause the solution to boil than it does for a pure substance. Okay. Moving on, properties of solutions, the fact that they have a lower freezing point. Okay, this is actually demonstrated with antifreeze. Okay, what does antifreeze do? It's a solution. Okay, we put it in our vehicles, and this solution causes things to have a lower freezing point. We don't want different solutions freezing in the pipes in our vehicle. So if we add some antifreeze coolant to our vehicle, it's going to lower the freezing point of different solutions in our vehicle. I mean, I forget what we add it to. We don't add it to like our gas tanks or anything. Is it like our... Oh, anyways, moving on. The other thing that you'll notice, you've probably seen this, why do we put salt on the roads when it ices? Okay, because salt added to pure water or ice makes it a solution. Okay, we have now made a solution of NaCl plus ice, which is water. Okay, so we made a solution of Na plus and Cl minus. And water. Okay, so we have this solution. We took pure water and we turned it into a solution, and we lowered the freezing point of it. Okay, when you do that. So what does this mean overall? Properties of solution. Essentially what we see is the lower vapor pressure, okay, that we talked about. A lower vapor pressure of solutions is responsible for both the boiling point elevation and a freezing point depression. Okay, that's the reason why boiling points are higher and freezing points are lower. It's because solutions have a lower vapor pressure, because again, there's just more glue, more intermolecular forces at play in a solution than in a pure substance. Okay, these things, elevated boiling point, a depressed freezing point, are known as colligative properties. So if you see that phrase, colligative properties, you need to think, oh, elevated boiling point, lower freezing point, because solutions have more intermolecular forces than pure substances. Okay, what is a colligative property exactly? I've given you examples of colligative property, but how do we define it? It's a property that depends on the concentration of a dissolved solute, but not its chemical identity. Okay, we don't necessarily care that we're adding salt to roads. It's just that salt is usually cheap, inexpensive. to add it, but it's just that we're turning that pure ice or water into a solution, and it's going to cause it to freeze at a colder temperature, so maybe the ice will become water and make roads more drivable. Okay, so again, this stuff is not the major things in chapter 9. I did want you to see it, but I'm going to move on to the last major topic,